Hello, I'm Carol Christian from the Space Telescope Science Institute, and welcome to this week's Hubble Hangout, which we've titled The Cosmic Dig in the Center of our Milky Way Galaxy. And before we start our discussion, I will introduce my colleagues Scott Lewis and Kelly Williamson, who provide all of the internet connectivity and the infrastructure and make this thing happen. The guests today are Annalisa Calamida from Space Telescope. She's a postdoc there, and also Kailash Sahu, who's a staff member at Space Telescope. And they've been doing some really interesting work on the center, well, the bulge of our galaxy, which we'll explain, and then these enigmatic objects called white dwarfs. So first I'm going to ask Kailash to explain what is the background of this program. Why were these observations taken, and then we'll get into the specific observations in a bit.
Actually, real quick, I'm going to let our audience know how
let the audience know how they can tweet and ask us questions.
Yes, absolutely. Right. So if you're watching us live right now, you'll be seeing on the bottom left of the screen here, there'll be some text that we're answering questions because we are. It'll open up a Q&A app, it's called, and you're able to type in your questions and submit them. You can also upvote other people's questions, and when we see a question that we're going to answer live, we select it, and it will timestamp it in the video, so for those that are watching after the fact can see when we're answering those questions. Also, I'll be live tweeting the event through Hubble Telescope, so you can follow us on Twitter at Hubble Telescope, and we'll be using the hashtag Hubble Hangout. So any questions or comments that you have for us over on Twitter, I'll be looking at those, sharing out the images that we'll be sharing here live on air, as well as checking out the YouTube comments. And I'm already seeing Q&A app stuff coming up there right now. So it's great to see you guys.
Great to have you guys out there.
And we'll be looking forward to interacting with you throughout the show.
Absolutely. Thanks, Scott. And thanks for reminding me. Okay, back to Kailash, who's going to explain the background of this project.
Okay, so the background of this project is this. This is a very large program with Hubble Space Telescope. The main idea for this program was to actually look for black holes. So black holes, neutron stars, white dwarfs, just through their what's called a micro-lensing signals. So black holes, just to give it very briefly, black holes, there in our galaxy there should be about 100 million black holes, there should be there, and out of which most of them should be just single, just single without any companion.
Right, so that's an important point because I think we've all heard about supermassive black holes that are in the center of galaxies, but these are different, right?
These are different. These are different in the sense, so these are just stars. Every star which starts with more than 20 solar mass ends up as a black hole. So those are the stellar mass black holes, which have only few sun solar masses. So those kind of things, there should be about 100 million of them. Thank you for explaining this. So I'm not talking of the supermassive black holes which are in the center of galaxies, but just stellar mass black holes. And there should be 100 million of them, as I said. And only 20 of them are actually known, and all the 20 of them are actually in binaries. So this is a program to find not a single stellar mass black hole, isolated one has been found so far, even though there should be 100 million.
So by binaries, you mean two stars that are associated with each other?
Right. So the one star...
Are they always, is a black hole and something else, or do we have two black holes sometimes?
Black hole and something else, because the way they found is just by looking at how the star, the binary star, the other star moves around this. Just from that, they infer the presence of the black hole.
So you said you're looking for them, and you're taking HST observations. They're black, right? So how do you find them?
So this is so that's the whole program. We will this is a clever program where we are actually not looking for light from the black hole. So it's essentially it's essentially you are using the Einstein's general theory of relativity. So if a black hole happens to be in front of another object, so the bulge, the galactic bulge, is one place where there are it's very crowded, lots of stars, and if one black hole happens to be just in front of another, then it will cause a brightening of this background star.
Oh, okay. Okay.
So this is called microlensing.
But that's not what you found in this particular study. You're looking for something else?
That is correct. So here, the main program was to actually look for these black holes. So for that, we need lots of observations. We need to monitor this bulge for 3 years, and of course Hubble has very high spatial resolution, and it goes very deep. So not only these black holes, but we can find so many other things. So what Annalisa did was actually to use this data set to look for white dwarfs, which are extremely faint, and actually they have not been found before, because not only they are extremely faint, but they also move differently compared to others. So you need to know, not only find these white dwarfs, but also know where they are. So that Annalisa probably will explain how it's
right. So you said that black holes came from massive stars. So I'm guessing that you're also going to say that white dwarfs are from not so massive stars. In fact, they come from stars like the sun, right? So maybe our star will end up as one someday. Not too soon, I hope.
I think we have a few billion years. I mean,
okay.
At least 5 billion. So
you don't have to worry about it.
Hopefully, by that time, when I'm in the singularity, I'll be on another planet by then. It'll be fine.
All right. Okay. So Annalisa, let's talk about the search for the white dwarfs and the strategy that you took to do that.
Okay. So as Kailash introduced the project, we are collecting this observation with the Hubble Space Telescope. And while I started to work on the data and analyze the data, I did a color magnitude diagram. Maybe we can show the graphic of a schematic Erskine-Russell diagram. And this is a tool that astronomers use.
So sorry, you want the colored one that shows the
the schematic color magnitude diagram.
Okay, the color magnitude diagram, which is in color, if we can find that.
So
yeah, there we've got it.
The HR diagram?
All right.
Yes, this one, exactly. Okay, so this is a very powerful tool that astronomers use to study stellar population. And actually, your stars, as you can see, are distributed along sequences. And what's in this graphic? So there is the brightness of the stars on one side, and on the horizontal axis, there is the temperature of the stars. So if you look on the left, there are very hot stars in blue. And if you look towards the right, there are cooler stars. And if you look at the top, there are the very bright stars. They're called supergiant and giants, while at the bottom, there are the really faint stars, like the white dwarf. So
and if you look really carefully, there's something called Barnard's star down to the lower right, and next to it, somewhere in there, should be the sun. There's a tenth of a mass of the sun, but the sun's in there somewhere.
Yeah, sun is more or less where the yellow region is, in the middle of what is called the mean sequence, because most of the stars are along the mean sequence, and they are just burning hydrogen in their core, in the center. So if, to look for white dwarf, you need to have very accurate and deep photometry, because as you can see from this diagram, the white dwarfs are much fainter than the sun and other stars, at least like 1,000, 10,000 fainter. And they're also very small, so they're really compact. A white dwarf is as big as a rocky planet, like the Earth. The radius is more or less 5,000 kilometers. So they are very, very small, and then they are surrounded by brother stars, so it's not a trivial task.
So anyway, wait a minute, so they're very small, but they come from stars that might be sort of like the sun, plus or minus a little. So how do they end up as white? I mean, why are they white dwarfs? What happened to them?
So yeah, the sun, as we were saying, will become a white dwarf, and the star that we observe now is white dwarf. There were sun-like stars, a little bit more massive. That's why they're already dead. And white dwarfs are dead stars, very, very ancient, very old stars, and they don't have nuclear burning anymore in their core. So it's the let's call it the final stage of stellar evolution for at least 90% of stars. So all the stars that have a mass less than more or less 8 solar masses, they will end up as white dwarf at a certain point. And what happens is that the hydrogen in the core of the star is burning, is producing helium. At a certain point, helium is burning as well, and is producing carbon and oxygen in the core of the stars. Most of the atmosphere of the stars surrounding the core will be lost during what is called the giant phase of the stars. Sometimes, while losing the mass, these stars they create nebulae, like planetary nebulae.
Those beautiful nebula that we see. So it pushes its atmosphere out when it loses all of its nuclear burning, and then we see beautiful nebula, but the little thing that's left is hard to see.
Yeah, the core. Actually, what is left is the core of the star that is made of carbon and oxygen, and this matter is contracting due to gravitational forces, because inside there's no nuclear burning anymore that is opposing to the gravity. So the core is becoming smaller and smaller and smaller, and is reaching the dimension of the Earth, of a small planet.
So how did you find first of all, why did you want to find these objects, and then how did you find them?
So why is because, as I was saying, 90% of the stars will end up as white dwarf, including our sun. So we want to study their properties to understand how, for example, the cooling process of these stars, how the cool down, how long it takes, their characteristics. If there are, like, for example, in some cases, some planets have been observed around white dwarf. So it could be that the planetary system around sun-like stars will survive this phase that I was telling you about, the giant.
Well, that's reassuring.
Yeah, it's reassuring. So it could be that the Earth will still be there around, the white dwarf, the sun white dwarf. So we want really to understand how these stars evolve, and then also because it means when you observe white dwarf, it means that this is a kind of old stellar population. So we knew that the bulge was included many old stars, so we knew that there were going to be some white dwarf in the bulge. But we were not
maybe we can now show that graphic that you had, which was to show people where, like, the galaxy and the bulge and the disk and all that, just so people get an idea of how how our galaxy is put together.
Yeah.
Where you're looking. So if you have that one.
The one showing the structure of the galaxy.
Yes. Although, well, let's keep going. I think Scott disappeared. So keep talking. Okay. Go ahead.
Oh yeah.
Which graphic would you like to see?
Yeah. The graphic with the it's the bulge and the disk. Although Scott found one that was higher resolution. So. Anyway, just we'll keep talking and it'll show up a bit.
Yeah, I can explain. So the bulge is actually is the center of the galaxy. It's the central region of the galaxy. And around the bulge there is the disk of the galaxy. And all around the galaxy there's what is called the halo, that includes stars, other stars, and includes also the globular clusters. And so our Milky Way bulge is actually the closest galaxy bulge that we can observe, because most of galaxies have a bulge, but of course the other galaxies are very far away, so it's really difficult to observe the single stars in these bulges because they are really faint, so we cannot go really deep and observe stars. While our galaxy bulge is 26,000 light years away, so it's still far, but we're still able to observe it. And another important point is that when you observe through the bulge, that is the center of the galaxy, we're observing through the disk. So we are observing through many other stars, the dust and gas that is in the disk of the galaxy.
Kailash, so is that the same reason that you were actually looking for the black holes in that region?
That's right. So what happens is, in fact, this is, as Annalisa said, so the galactic bulge, we are actually looking through the disk. So if the disk also has lots of stars, and in fact, the disk has not only lots of stars, but it will also have dead stars like white dwarfs, neutron stars, and black holes. So what happens is, when we are observing those stars in the galactic bulge, then if there are black holes in the disk or even in the bulge itself, in the nearer portion of the bulge, then they can line up. They would come in front of one of those background stars. So then we would see a brightening. Actually, we have seen lots of brightening, though we have actually detected lots of them already. So
if you looked in some other direction, there wouldn't be so many background stars, and so they might be there, but you wouldn't be able to detect them as easily.
So the probability, what happens is, there are two things. One is what's called the optical depth, means the probability that one of them will be actually lensed by an object is roughly 1 in 300,000. Okay, so that means we need to have at least 300,000 stars to be able to see one of the events. Right. So we are actually monitoring 3 million stars. So the bulge is so dense. Every field we are monitoring about 12 fields, and each field has roughly, fields has about 300,000 stars.
Wow, that's nice.
So that means at any given time we have 10 events going on. Of course, out of these 3 million stars, but so we have all the technique to be able to detect, and we have detected.
Wow, that's amazing. Okay, so Annalise, back to the white dwarfs, and while you're talking about why you're interested in them, there is someone who asked on the Q&A asked about the composition of the stars, and I know that that's an important part of the research question.
Yeah, so as I was saying, most of the dwarfs have a core of carbon and oxygen, while they have a very, very thin atmosphere that is composed mostly of hydrogen and a little bit of helium. But in this side of the bulge, actually, from at least the color distribution of the white dwarf from the Coromagnon diagram, maybe we can show the graphic, right? Okay, we cannot show the Coromagnon diagram.
Kelly might have it. The black and white graphic, do you have that?
The color magnitude diagram.
Oh, the color magnitude diagram. But these are suspected to be older, right?
Yes.
For older stars? Oh, okay. Okay,
this one. Yeah, so the white dwarf, as we were seeing in the schematic color magnitude diagrams, are hotter, so bluer, than the majority of stars that are main sequence stars on the right, on the nice sequence on the right. But the color distribution of the stars can give us clues on their core composition, because if the core of these stars is made of helium, for example, they will have they will become redder, so they will move towards the main sequence. As you can see in this color magnitude diagram, there is a dispersion in the color of the white dwarf main sequence.
So that's the width of
It could be that a fraction of the stars in this study, we estimated more or less 40% of these stars could be helium core white dwarf. And of course, we cannot really say which one is an helium core white dwarf and which one is a carbon oxygen core white dwarf, because we didn't measure the abundances. But just from the color information, we can say that probably there is this fraction of helium core white dwarf. And why is this important? It's because helium core white dwarf theoretically shouldn't be dark. So from stellar evolution theory is saying that helium core white dwarf will take more than 30 billions of years to form, because they come from the very low mass stars.
Okay, so it takes a long time.
Takes forever. So the stars that will become helium core white dwarf, they are still burning hydrogen in the core, and they're still very small sun, like 0.3, 0.4 solar mass stars. So they cannot be helium core white dwarf. So why are we observing them? So this can happen when, again, there is a binary system.
So I was just going to point out that for folks, that the more massive stars, some of which that become a black hole or a neutron star, they're very big and they live fast and die hard in a sense. So they burn their hydrogen, they can become a supernova, whatever, and they do that very fast. But happily, stars like the sun or anything less than solar masses, 8 solar masses, then lives more slowly. So it takes a longer time to produce these white dwarfs. Is that what you're saying?
Yeah. So for example, the sun, we know that more or less the sun has 5 billion years, and we know that it's still burning hydrogen in the core and still in equilibrium.
And it'll be around for a while.
And we're still here and fine.
We're
But
only halfway.
And the sun is one solar mass stars. So stars that are smaller than the sun will live much longer than the sun. So it takes really billions of years to finish the hydrogen fuel. And so for helium core white dwarf, we need a different process, formation process, and probably it's just a binary system. So the binary star is stripping part of the mass of these sun-like stars, let's say. It's losing a lot of mass. And then at the end, it's not able anymore to burn helium in the core. It doesn't have enough mass to contract and then to reach the high temperature that I need to burn helium in the core. So the core is mainly an helium core. And why white dwarf and equilibrium? If there is no nuclear burning, they should just collapse and become neutron star or black hole. But no, there's something that is preventing the stars from, is preventing the gravitational collapse that is called the degenerate electron pressure.
So if they were by themselves without the binary, then they would become a white dwarf faster, or something else, a black hole. But the binary has something to do with how they evolve.
So if they were not in binary, they will become normal, what we call now normal white dwarf. So carbon acid core white dwarf. But they became helium core white dwarf because they were in a binary, probably. Now I was saying that just the existence of white dwarf is proving that the existence of this electron degenerate pressure that is keeping the star in equilibrium. Otherwise, there won't be any force that contrasting the gravitational force, and the star will collapse and will eventually become a black hole.
So maybe we can show some of the images from the data. Maybe you can say what we should look at, because we're interested in what does the Hubble data look like, and how did you find these? Because I know this was a pretty ambitious thing to do. And so we're getting an interesting mix of the Hubble graphic and the image. I think we need to maybe try that again. Anyway, there is an image of with the white dwarfs identified. Kelly, we're getting both the Hangout graphic and the image at the same time.
Okay.
Okay.
Okay. Yes.
Okay.
So these are some postage stamps from our ACS composite image. So it's called a three-color image and should show more or less the color of the stars. So some stars are redder because they are cooler, and some stars are bluer because they are hotter, as we were showing in the diagram before. And we know that white dwarfs are really hot, so they are the bluest of the stars, but they're also very faint. So from this graphic, you can see how the blue color is evident, but it's also that if they are really faint, so that sometimes they can be hidden by brighter stars. So as you can see here on the bottom left.
So these little blue things, it's kind of in the center, that's the star?
Yeah, that's the star. So as you can see in the bottom left image, the star is almost disappearing in the bright wings of the very bright stars. Probably the bright stars belongs to the disk. It's one of the bright stars in front of us. So while we are looking towards the center of the galaxy, we have all these stars, very bright in front of us. Okay, this is the bigger image here. So the difficult task was
Kelly,
really
is it possible to show the one where it has the whole field and then these are on the side? I don't know exactly what's going on with the screen share, but I know there's an image that shows the whole field. Maybe we can try to find that, because I'm seeing it in the background. That's what's weird.
I don't see
well, I'm seeing a double exposure, which I
actually see on the left the big image, and on the right you see the 16 small.
Oh, do you?
Images. Yeah, I see that.
Right, I don't see that. Right, I hope everybody sees that. Okay, good.
Yeah, so on the left you have, let's say, what you actually see if you open your images, and you see all these stars, brighter and other, they are fainter, and some are red and some are blue. And so the important thing is to go deep, because we are seeing white dwarf really deep. As you can see on the right, the blue stars in the center, they are the white dwarf.
No, these are the white dwarfs because of the color. Oh, okay.
Yeah, okay, this is the bigger.
Yeah. So now this is a nice one that calls out the white dwarfs.
Yeah.
I'm amazed that you can find these.
Yeah.
I'm just amazed because this is, as you said, it's very, very crowded field. So talk a little bit, Kailash, let's get you back in this. So how do you find these little blue things in this star field?
You know what? See, this one of the main thing was we were helped by the fact that I had another program in 2004, actually the same field, to look for planets. We actually discovered 16 planet candidates in the same field.
Okay.
So the same field, actually we had observed. It was also a large program to actually detect exoplanets, planets around these stars, and that we observed continuously.
If you can put that back up, that'd be great. We're amazed by this image. If you don't mind putting it back up.
So anyway, that field we observed with Hubble Space Telescope continuously for 7 days, and we find that was a program to find planets. We did find 16 of them, as I said, but. So the fact that we had observed the same field in 2004, and now we are observing the same field and many other as well, but one of them is the same field also now, allowed us actually to see the motion of these stars. Actually, generally when people look at stars, they are fixed in the sky, they think, but actually with Hubble's resolution, you can see that the stars move in these span of 8 years. So that was one of the main things. I think there is a movie later on. Maybe
yes.
Yeah.
You can see how the stars move.
How actually the stars move. So if you compare you will see a bit later, I guess. So you will see that the stars actually move, and the stars which are in the disk, they move differently compared to the stars which are in the bulge. So that's one of the main things. Not just the blue part of this, but also how they move. Because in principle, even with ground-based telescopes, people could see at least some of these blue stars, right? But they never know whether it belongs to somewhere in the disk or it is far away in the bulge, that they could never tell. Whereas our program, the fact that we had one observation in 2004 and one observation now, allowed us actually to see which ones actually are there at 26,000 light years away. So that was one of the key things. So we looked for both the blue color and the faintness, as well as how they move. So by combining these two, we can actually tell that they are white dwarfs in the galactic bulge.
Oh, okay.
Yeah.
And then you have colors too?
Right.
Yeah. So that's part of it.
Right. So we observed both in two bands, one in the visual, what's called the 606W, the visual band, another is slightly to the red part of the spectrum. So these two bands, we observed in two bands, and so comparing these two, we can see which ones are the blue ones. So this color magnitude diagram you saw.
Okay, but that's our really big field. So you can't be doing this by eye. Please explain how this works. How does this work? How do you find these things?
Actually, you can do this by eye. Okay, listen.
Well, many days in a row.
No, of course not. So first of all, this movie is showing stars move a lot in 10 years. They move, as you can see in the movie. This has been done with an image taken in 2004, one in 2006, one in 2012, 2013, and 2014. And so first of all, we selected the stars for the motion. Then we selected the star in magnitude and color from the color magnitude diagram. And then I actually went back to the images to actually check every single star. So we started from a sample like a few hundreds, like 200 or 300 stars, and then I checked all of them, and we did photometry again, and then to be sure that they were really white dwarf, or maybe, and the point was to have a good measurement of the stars. So
not all the stars, but just the white dwarf candidates.
Yeah, good measurement of these candidates. So some of them, of course, the sample is not complete, but we wanted to be sure to have a well-measured white dwarf, and we wanted to be sure that they were part of the bulge. So that's why now in this study we ended up only with 70 stars out of like probably thousands of white dwarfs that are in this small field of view that has been observed with ACS on Hubble. So we estimated that probably the number is like 100,000 stars. Most of them, they are really faint that not even Hubble is able to detect them.
Oh, okay.
So we'll have to wait probably for the future facilities like JWST, the High Definition Space Telescope, or the future ground-based extreme large telescopes to really go deep, so deep, and to have the more spatial resolution to actually separate these very faint stars from the rest of the stars and to measure their motion. And so to actually see thousands of white dwarfs in this field. So this is only the peak of the iceberg.
Okay, so we talked about the program, and we talked about that you were looking for the white dwarfs, and then you found them, and so the answer is?
Yes.
What did you learn?
Yeah, we learned that actually white dwarfs are there in the galactic bulge, confirming that this is an old stellar population, and we learned that part of these stars probably have a different composition, the core, the helium core white dwarf, and so probably they were binary. So this also gives us a hint of the binary fraction of the bulge that nobody really studied up to now, because it's really, as we are saying, it's really difficult to study stars in the bulge. They're far away. There is dust in front of us, and things like that.
So they are binaries.
Some of them, yes.
About 30 to 40% of them are binaries.
And so we know that actually many stars in the bulge can be in binaries, and we said that in the field at least 50 or 60% of stars are in binary systems. So it looks like the bulge in this is similar to the disk. And then we can study other properties because, as we are saying, white dwarfs are clocked. They are clocked because they just cool down. They lose thermal energy. They cool down. They become fainter and fainter and cooler and cooler. And so this is a kind of clock that can give us a hint on the age of the stellar population. So when we will be able, hopefully, with the future facilities to, for example, to go deep in the white dwarf cooling sequence, we can use this sequence to give an age to the bulge. And now we can use other tools to age the stellar population of the bulge.
Sure. So you want to look at many methods, but this gives one kind of information about the age of the bulge, because the bulge is important because you want to know how the galaxy formed.
Yeah, we want to know when exactly the bulge formed, if it formed in a really short time, or if it took a longer time, a little bit longer time. Because we want to understand it's part of the Milky Way formation. And up to now, there are like different theories on the galaxy formation, but especially on the nature of the bulge. So some scientists claim that the bulge it's a classical bulge that formed like through gravitational collapse.
And it's very old.
It's very old, and it's at the beginning when the cloud from which the galaxy formed. The cloud of material just collapsed like this, and the bulge formed at the beginning very quickly, so all the stars must be extremely old in the bulge. While some other theories say that the bulge is more like a pseudo-bulge, and so the stars in the bulge started to form at the beginning many years ago, but then other stars were keep forming in the bulge, and then so the bulge was kind of evolving. And so
you might expect to see a mixed population then, not just one type, but a mixed population.
Population.
So if I can add a bit.
Sure, please.
So what happens is that now we know from these, and also some from earlier observations, we know now that these white dwarfs now, they age between 13 billion years to 11. So they all formed within about 2 billion years. And they can be just as old as the galaxy itself. Okay. So these bulbs formed about 13 billion years ago, and star formation stopped about 11 billion years ago. So the entire bulge formed within about 2 billion years ago. Whereas we know that in the disk, the star formation is going on even now. So this, even now, I mean, there are, Orion, the star formation, and many other star forming regions. So this tells us that the bulge forms first. and then so it's a fundamental thing where how the galaxies form. It tells us that yes, indeed, the bulge forms first, and it forms pretty quickly, and then the entire whole structure of the galaxy that builds on. So it takes much longer to form the entire galaxy. So this is the more a general picture.
So the center part forms, and then the disk forms later, either through getting material or collisions or anything.
The center
like that.
part forms rather quickly. So it forms within, at least in our galaxy, it formed within 2 billion years. So.
Wow. So, okay, so the James Webb question. So would we expect then, as we look back, either with some Hubble observations, but mainly with, like, for example, James Webb, that we would maybe, as we look back in time, see that epoch where bulges are forming, but there's no disk yet? Will we be able to see that, do you think? We'll see objects that are just mostly bulge?
So just to back up a little bit, okay? So
okay.
If I may, okay. So see, one thing is here, what we see actually are the very young white dwarfs. Means the white dwarfs, they become fainter and fainter as they become older, right?
Okay.
So
yes.
we actually, as the red giant, it becomes white dwarf, and then it starts cooling and becomes fainter and fainter. So we detect only the top. That's what analysts have said. The iceberg, the top of the iceberg, because we find only the very youngest white dwarfs. We don't know what happens far down when they become when they become extremely cold. At what happens at that we have not reached yet, even in our own galactic bulge itself. And so that would be James Webb. We may be able to actually get all the way to this what's called the blue hook, which will get the age of the galaxy itself, right? So that's one. And then whether we would be able to go all the way to when the bulge just formed, when we James Webb Space Telescope, we can go look at redshift 4 or 5 at that point when actually just the bulges are forming. Yes, in that's definitely one of the aims of JWST, to be able to see the very youngest galaxies where they're just being formed, where the bulges are just being formed. Yeah, that would be pretty cool to be able to see.
So another question for Annalise. So you were talking about you identified white dwarfs that were associated, that you're confident are associated with the bulge, but you said there were other ones you found as well. So do you know that they're not in the bulge, that they're either near the center of the galaxy or they're in the disks, and have they told you anything yet about their population?
So I was saying, let's see. Yes, there are. We also saw some white dwarfs that were actually part of the disk population. So they were brighter and they had a different motion. So we actually excluded them. And the point was that to actually be sure that the white dwarfs we were sending were part of the bulge, we had to do a selection in this motion. And by doing this selection, we had to cut more or less 70% of the stars that actually belonged to the bulge, and so also to the white dwarf bulge population. The point is that we have those stars. We know that we can see those stars, but if we cannot be sure that they belong to the bulge or the disk population, we cannot really say much. So we didn't include them in our study. Carol?
Okay.
Okay, I don't see you anymore.
Oh dear. Okay, we are. All right.
Yeah, we are losing.
Oh no. Oh no. Okay. Oh gosh. All right. Let me get back in.
We can still hear you very clearly, Carol.
Yeah. You can. Okay. Then I'll just keep talking. Yeah, I lost video too. Scott lost video. Actually, I've got some people on the Q&A that lost video. So one question from the Q&A. I know there are other questions, but one question that was asked was just can either of you talk again about this idea that the binaries are important? That both either for white dwarfs or black holes, and the fact that stars can form white dwarfs or black holes by themselves, but sometimes they form in binaries. And do we know what fraction of stars do this in binaries, or do we have any information about that? And can we actually discover black holes on their own?
Okay, so so this is a very good question, actually. So this is one of the main things that for black holes. Let's first go to black holes and then we'll go to white dwarfs. See, so far there have been 20 black holes have been detected, and they are in binaries. So one is a black hole, another is a star. So to go back, to start with the thing that all stars, say about 50% of the stars are actually binaries. That's what general statistics is. So then start with, let's say, massive stars, because massive stars are the ones which become black holes, right? Now follow the logic. It is a little complicated logic, but so try to follow the logic. So stars, half of the stars are in binaries.
Okay.
Then the massive stars are, let's say, massive stars actually are roughly same percent, maybe little more of them. So let's say massive stars also have 50% of them are binaries. Okay.
Okay.
Now,
for the sake of argument, okay.
So let's say 50% of massive stars are binaries. Now, as the star evolves, so the binary can be the star and the massive star and the binary companion. That distance can be anything. They can be close by or they can be far away. Okay. Now let's assume, take the ones that are close by. Okay. First, let's say ones that are close by. Then what happens? The massive star, when it becomes a supernova, and when it is about to die, what happens is it becomes so large that it actually envelopes the other one too. Because so if it is close by, so if the binary companion is close by, then the massive star, as it evolves, it engulfs the other star. So it becomes one. Okay.
Wow. Okay. So
it ends up as a single one. Now, so that's the one which is close by.
The close ones, right? But they're not always close.
Right.
So
now let us say which ones are far away. Now the far away, what happens? So the one is the massive star, the other one is very far away. So as the massive star now becomes a big and it becomes a supernova, then the supernova, then as it collapses, it gives itself a kick. It's what's called the kick velocity, because the explosion is not symmetric. So then it gets a kick. So since the companion was far away, they were moving rather slowly around each other. When it is far away, they don't move very fast around each other. They move rather slowly.
But so now one of them got a kick.
One of them got a kick. So that means they separated out. So they ended up as single. So the ones that are close by, they ended up as single. The one that was just far away ended up again as single. Okay? So the ones that are maybe somewhere in between, they might still remain as binaries, and those are the ones, some of them, 20 of them have been found. But if you see, so most of the black holes, as we think, maybe are single, not binary, not in binary. Okay. And that's why there should be 100 million of them, and we still don't know, haven't detected even single one. Actually, well, our program is the only one actually may find them. But so that's the binary so far as the black hole. Now, so far as the white dwarf binaries, do you want to tell Annalise?
Yeah, so Annalise can tell us about the story of white dwarfs.
Right.
Okay. Yes. So as we're seeing, 50% of the stars, you said that more or less 50% of the stars, or even more, are in binary systems. So even white dwarf can end up in binary systems. And for example, these systems are really important because some of them are actually the progenitor of what we call type 1a supernovae. that are very important because now they are used as standard candles to measure the distances in the universe, and not only distances, but how much the universe is accelerating in its expansion. So this finding brought to the Nobel Prize of 3 astronomers that got the Nobel Prize in 2011. So it's really important to study wave dwarf in a binary system because we want to understand what happens before for example, the supernova explosion. So what happens? In some cases, we have a system where we have two wave dwarfs. And at a certain point, they orbit around each other, they can spin off, and at a certain point, they can merge. And why do they explode? Because there's a fundamental limit, as I was saying before. The wave dwarf rely on what is called the electron degenerate pressure. And this pressure works in contrast with the gravitational force until a certain mass that is called Chandrasekhar mass, from the name of the astronomer that found this theoretical limit. And it's around 1.4 solar masses. So if you put together two wave dwarfs that are more massive than 1.4 solar masses in total, then the star cannot survive as a wave dwarf. So it will collapse, and in collapsing, then it will explode as a supernova. So this can happen. Otherwise, it happens that there is a wave dwarf and the companion is not a wave dwarf. It could be, for example, normal main sequence stars. And so the wave dwarf is accreting matter for these other stars, is accreting and feeding, and sometimes by accreting matter, then it will again surpass the Chandrasekhar mass limit and then will again explode. Sometimes they don't explode, but we observe them as what we call dwarf novae. So they are stars that increase the luminosity by a lot, and so since, as we are saying, they are really faint, at a certain point where there was a very faint wave dwarf, you see a very bright stars, and then the stars disappears again, and then it comes back again, and then it disappears. So, and this increase in luminosity can last like 1 month, and we actually found a couple of these dwarf novae in our Hubble study. We found a couple of them, and yeah, I'm sorry, but now I didn't send you the movie. I also had the movie where we could see the stars actually increasing luminosity.
Yeah, they're very interesting.
They're really interesting. So this the finding of two of these dwarf novae in our field is further confirming that there are some wave dwarf in binary systems, because we actually see them, and these were part of the bulge stellar population.
And they create these unusual situations. Okay, so we're coming up on it. So Scott, I'm
back.
You're back. Congratulations. My video still doesn't work, but that's okay.
So my internet's out. I'm tethering my phone. So
all right. That's good. We're glad you're here. I just wanted to know, so we talked about the composition of the stars, and we talked about binaries, both those that make black holes and the ones that make white dwarfs. So I think I've got all the questions from the Q&A app. I don't know if there's anything else out there, any other questions for our authors?
I'm getting Twitter pulled back up because it's an adventure. So you got the composition of those early stars,
and the binary black holes and the binary white dwarfs, and we talked about great. So I think we've covered all the questions that I have.
Let's see here. I'm not seeing anything else. I'm seeing a lot of great activity as far as people liking and retweeting. People are loving that HR diagram that helped explain what's going on and how the stars work, so that's also great. I'm being told to hack the planet, and I just did, which is why I'm back. So thank you. Yes. Thank you to Buffro. Let's see here. No, again, just a lot of really great activity as far as people interacting with us on Twitter and getting the word out. The only thing I'm seeing, too, is just people having YouTube problems, which I would look into later.
Yes, I had a couple of those reports, too, although people are apparently able to listen to us, so that's good. So anyway, well, that's great. Very interesting. So the question we always like to ask is, what's next? Are you looking for more white dwarfs? I know Kailash has a program looking for microlensing. What happens next in this line of research? What do you hope to do?
So, as I was saying, we presented the result of only one of the 12 fields that we actually observed.
Oh, okay.
Yes. So we have other 11 fields. And Yeah, but we had to wait until the observation were over, actually at the end of last year, because we need, as we are saying, we need a long time baseline to be able to accurately measure the motion of these stars. And if we can measure the motion, we can really separate the disk stellar population from the bulge stellar population. So now we will try, of course, to identify the bulge dwarf pooling sequence in the other fields as well, and this will help us because, of course, we will increase the statistics. So instead of having 70 stars, we will have hopefully at least 1,000 stars. And so we'll keep going, in our study for sure, and then we're looking forward to JWC to come and to be able not only to go deeper in the study of the red dwarf, but also, for example, to collect spectra of this red dwarf, because we are also interested in the composition of the atmosphere of these stars, but also in estimating the actual mass of these stars. And this has been done for red dwarfs that are close by, like for example in the disk. They have an estimate of the average mass of the red dwarf that is 0.6 solar mass.
But you want to do it for the other ones.
But we want to do it for this faraway red dwarf, but we don't have. They are really faint, and so nowadays we're not able to collect spectra to estimate the mass of these stars. So,
Kailash, any parting words?
Yeah, so see, this is as Annalisa said. So we have used this data set, which were for many other things that what the program's main aim is. So the program's main aim is to look for microlensing, and of course these were also part of this, to look for white dwarfs, to detect white dwarfs and the initial mass function and them too. But so we expect to detect about 100 of these microlensing events, out of which some of them would be white dwarfs, neutron stars, black holes. So that will tie in very well with this. So here we are looking, so right now we are looking for white dwarfs through their light, whereas the microlensing, even if it is a very old white dwarf, however faint it is, it doesn't matter, because all that it cares is the gravitational effect of that. So there we would be sensitive to detecting all white dwarfs and neutron stars and black holes. So that would be, we would not find lots of them because they have to line up with the background stars. But that statistics of that would tie in very well with what we found already. So the young white dwarfs versus the total number. So we expect to find a sample of white dwarfs, neutron stars, and black holes through microlensing as well. Which will tie in very well with this study, and then we should know how frequent, how common are these the dead stars, the white dwarfs, neutron stars, black holes are in this field.
Well, you have your work cut out for you.
And can I add something? In microlensing, we also give us an estimate of the mass, a very accurate estimate of the mass of the white dwarf.
Yes.
That's another point.
Yeah, absolutely.
The mass of the white dwarf, neutron star, and black hole.
Which is important.
Yes. Absolutely. So the microlensing is, our program is designed so we will detect not only just, of course, we detect, but detecting, we would also see not just light amplification, but how it causes a shift in the position because of this, just by the deflection of light. So that will tell us the mass of the lens, the white dwarf, neutron star, or black hole, and also the distance to this. So we will know the distance.
That's important.
So because the distance will come from this parallax measurement from the microlensing. So
well, you'll come back and talk about that as well. So we're coming up on the hour, and I want to thank our guests and our viewers very much. And Scott and Kelly for pitch hitting with some of the infrastructure problems we had. I know people were curious where Tony is. Right now, he's off working on some new ideas, entrepreneurial ventures that he's involved with, and he's taking some traveling time. But don't worry, Tony will be back, I'm sure, in the future. And I'm glad everybody tuned in, because this was a really great hangout. And we'll probably see you next week. I think one of the other multi-treasury programs might have some interesting news, so we're going to follow up with them and see if we can do a hangout with them.
Yes.
So thank you very much. All right. Okay, take care, and thanks a lot, and hopefully we'll see you next week.
And as always,
keep looking up. This particular study, you're looking for something else?
That is correct. So here, the main program was to actually look for these black holes. So for that, we need lots of observations. We need to monitor this bulge for 3 years, and of course Hubble has very high spatial resolution, and it goes very deep. So not only these black holes, but we can find so many other things. So what Annalisa did was actually to use this data set to look for white dwarfs, which are extremely faint, and actually they have not been found before, because not only they are extremely faint, but they also move differently compared to others. So you need to know, not only find these white dwarfs, but also know where they are. So that Annalisa probably will explain how it's
So you said that black holes came from massive stars. So I'm guessing that you're also going to say that white dwarfs are from not so massive stars. In fact, they come from stars like the sun, right? So maybe our star will end up as one someday. Not too soon, I hope.
I think we have a few billion years. I mean,
at least 5 billion. So
you don't have to worry about it.
Hopefully, by that time, when I'm in the singularity, I'll be on another planet by then. It'll be fine.
All right. Okay. So Annalisa, let's talk about the search for the white dwarfs and the strategy that you took to do that.
Okay. So as Kailash introduced the project, we are collecting this observation with the Hubble Space Telescope.
The event through Hubble Telescope, so you can follow us on Twitter at Hubble Telescope, and we'll be using the hashtag Hubble Hangout. So any questions or comments that you have for us over on Twitter, I'll be looking at those, sharing out the images that we'll be sharing here live on air, as well as checking out the YouTube comments. And I'm already seeing Q&A app stuff coming up there right now. So it's great to see you guys.
Great to have you guys out there.
And we'll be looking forward to interacting with you throughout the show.
Absolutely. Thanks, Scott. And thanks for reminding me. Okay, back to Kailash, who's going to explain the background of this project.
Okay, so the background of this project is this. This is a very large program with Hubble Space Telescope. The main idea for this program was to actually look for black holes. So black holes, neutron stars, white dwarfs, just through their what's called a microlensing signals. So black holes, just to give it very briefly, black holes, there in our galaxy there should be about 100 million black holes. There should be there, and out of which most of them should be just single, just single without any companion.
Right, so that's an important point, because I think we've all heard about supermassive black holes that are in the center of galaxies, but these are different, right?
These are different. These are different in the sense, so these are just stars. Every star which starts with more than 20 solar mass ends up as a black hole. So those are the stellar mass black holes, which have only few sun solar masses. So those kind of things, there should be about 100 million of them. Thank you for.
Hello, I'm Carol Christian from the Space Telescope Science Institute, and welcome to this week's Hubble Hangout, which we've titled The Cosmic Dig in the Center of Our Milky Way Galaxy. And before we start our discussion, I will introduce my colleagues Scott Lewis and Kelly Williamson, who provide all of the internet connectivity and the infrastructure and make this thing happen. The guests today are Annalisa Calamida from Space Telescope. She's a postdoc there, and also Kailash Sahu, who's a staff member at Space Telescope. And they've been doing some really interesting work on the bulge of our galaxy, which we'll explain, and then these enigmatic objects called white dwarfs. So first I'm going to ask Kailash to explain what is the background of this program. Why were these observations taken, and then we'll get into the specific observations in a bit.
Actually, real quick, I'm going to let our audience know how they can.
Let the audience know how they can tweet and ask us questions.
Yes, absolutely. So if you're watching this live right now, you'll be seeing on the bottom left of the screen here, there'll be some text that we're answering questions because we are. It'll open up a Q&A app, it's called, and you're able to type in your questions and submit them. You can also upvote other people's questions, and when we see a question that we're going to answer live, we select it, and it will timestamp it in the video. So for those that are watching after the fact can see when we're answering those questions. Also, I'll be live tweeting.
Explaining this. So I'm not talking of the supermassive black holes which are in the center of galaxies, but just stellar mass black holes. And there should be 100 million of them, as I said. And only 20 of them are actually known, and all the 20 of them are actually in binaries. So this is a program to find not a single stellar mass black hole, isolated one has been found so far, even though there should be 100 million.
So by binaries, you mean two stars that are associated with each other?
Right. So the one star.
Are they always is a black hole and something else, or do we have two black holes sometimes?
Black hole and something else, because the way they found is just by looking at how the star, the binary star, the other star moves around this. Just from that, they infer the presence of the black hole. So you said you're looking for them, and you're taking HST observations. They're black, right? So how do you find them? So this is so that's the whole program. We will this is a clever program where we are actually not looking for light from the black hole. So it's essentially you are using the Einstein's general theory of relativity. So if a black hole happens to be in front of another object, so the bulge, the galactic bulge, is one place where it's very crowded, lots of stars, and if one black hole happens to be just in front of another, then it will cause a brightening of this background star.
Okay.
So this is called the microlensing.
But that's not what you found in this.
And while I started to work on the data and analyze the data, I did a color magnitude diagram. Maybe we can show the graphic of a schematic Hertzsprung-Russell diagram. And this is a tool that astronomers use.
So sorry, you want the colored one that shows the
the schematic color magnitude diagram.
Okay, the color magnitude diagram, which is in color, if we can find that.
So
yeah, there we've got it.
The HR diagram?
All right.
Yes, this one, exactly. Okay, so this is a very powerful tool that astronomers use to study stellar population. And actually, your stars, as you can see, are distributed along sequences. And what's in this graphic? So there is the brightness of the stars on one side, and on the horizontal axis, there is the temperature of the stars. So if you look on the left, there are very hot stars in blue. And if you look towards the right, there are cooler stars. And if you look at the top, there are the very bright stars. They're called supergiant and giants, while at the bottom, there are the really faint stars, like the white dwarf. So
and if you look really carefully, there's something called Barnard's star down to the lower right, and next to it, somewhere in there, should be the sun. There's a tenth of a mass of the sun, but the sun's in there somewhere.
Yeah, sun is more or less where the yellow region is, in the middle of what is called the mean sequence, because most of the stars are along the mean sequence, and they are just burning hydrogen in their core, in the center. So if, to